In a previous video, I talked about basic periodic trends involving atomic radius, first ionization energy, and electronegativity. This time we're going to go into some more advanced concepts in periodic trends, and these are going to include the ionic radius of atoms, additional aspects of ionization energies, and electron affinity. So let's start with ionic radius, and we're going to discuss both cations and anions. Remember that cations are neutral atoms that have lost electrons and therefore now have a positive charge. Metals typically are going to do this, so let's take a look at magnesium. This is a neutral magnesium atom. Typically speaking, when metals lose electrons, they're going to lose all of their valence electrons. So magnesium has 2 valence electrons, and so when it becomes an ion, becomes the magnesium 2+ ion, it will lose those 2 valence electrons. After these 2 valence electrons are lost, the atom loses its entire third energy level, reducing the size dramatically. Therefore, we can see that when atoms lose electrons, their radius tends to decrease significantly. Now let's look at anions. Anions do the opposite. An anion is when a neutral atom has gained electrons and therefore now carries a negative charge. Since nonmetals typically do this, we'll use fluorine as an example. Fluorine starts off with 7 valence electrons on that second energy level. When it gains an additional electron, it'll add it to that shell. Unlike with the cation, where we lost an entire energy level, the anion adding an additional electron didn't give us an extra energy level, so at first it may look like nothing's changed about the size. But what we have to consider is that while the attraction to the nucleus hasn't changed specifically, the fact that we've added another electron to this energy level means we have 8 electrons there instead of the original 7. And electrons repel each other, and since we've got this extra repulsion going on, these electrons will push each other further away. And by pushing each other further away, we're going to expand that outer energy level a little bit, pushing those electrons a little further away from the nucleus. This will cause the size of the atom to increase. So as a general rule, when atoms gain electrons, they tend to increase their atomic radius. Okay, so now let's talk about ionization energies. The last video I did, I talked about just first ionization energy, and first ionization energy is the energy necessary to remove the first electron from an atom. But there's an ionization energy for every electron that's in the atom. So hydrogen only has 1 ionization energy, but helium has 2 ionization energies because it has 2 electrons. Magnesium has 12 ionization energies because it has 12 electrons. To remove the first electron from a mole of magnesium atoms requires 738 kilojoules. But to remove the second electron from a mole of magnesium atoms requires 1,451 kilojoules of energy. This increases because once we remove that first electron, remember we have less repulsion going on in that outermost energy level, which means the electrons do actually get pulled in a little closer. Remember that cations are always going to be a little bit smaller than the original neutral atoms. This means that it's going to take more energy to pull that second electron away because it's being held a little closer and more tightly to the nucleus than the first electron was. Now, when we go to remove the third electron from a mole of magnesium atoms, we're going to find that the energy significantly increases to 7,733 kilojoules for that third electron. This is a huge increase over that second ionization energy. But if we look at the Bohr model of the magnesium atom, it becomes very apparent why that third ionization energy is so much larger than the first two. The first and second ionization energies deal with taking those 2 valence electrons away from the magnesium atom. These 2 electrons only have an effective nuclear charge of around +2. However, once those 2 valence electrons are gone, we're left with only 2 energy levels. And on that second energy level, because it only has 2 shielding electrons against those 12 protons, the effective nuclear charge jumps up to +10 for those electrons. And this is where we're trying to take that third electron from. So you're really fighting very hard against the nucleus to get this third electron away compared against those first 2. And you're just going to see that these values just get higher and higher and higher as you go. For instance, magnesium's 4th ionization energy jumps up to 10,540 kilojoules for a mole of magnesium atoms. This sort of trend will happen with all of the atoms. As you remove electrons from them, once you pass the number of valence electrons and you start pulling from the energy level below that original valence shell, you're going to see a skyrocket in the amount of energy it takes to remove electrons. So now let's talk about some anomalies with ionization energies. We talked about how the general trend with ionization energies as you go from left to right across a periodic table is that you're going to see an increase in ionization energy because the effective nuclear charge is getting larger. So let's look at the first ionization energies of a few elements in the same row. Let's look at the third row on the periodic table: sodium, magnesium, aluminum, silicon, and phosphorus. Sodium's first ionization energy to remove that first electron is 496 kilojoules per mole. Magnesium, as we saw previously, has a first ionization energy of 738 kilojoules per mole. Now, so far, this works with our trend, because as we said, as we go from left to right across the table, our ionization energy, that first ionization energy, should be increasing. So let's look at aluminum. Well, when we hit aluminum, aluminum goes to 578 kilojoules per mole for the first ionization energy, which is actually a decrease compared to magnesium. And our trend says that we should be increasing as we go left to right. Let's see if this continues when we look at silicon and phosphorus. As we can see, silicon increases to 786 kilojoules per mole, and phosphorus increases to 1012 kilojoules per mole. So silicon and phosphorus do continue the trend. Aluminum's the one that seems to break the trend for some reason. And in order to understand this, we actually have to look at the quantum mechanic model of the atom. Once we look at the electron configurations of these 5 atoms, we start to see why this anomaly occurs. Sodium and magnesium are losing their electron from the 3s sublevel. On the other hand, aluminum has to lose its electron from the 3p sublevel. 3p electrons, you may remember, are higher energy electrons than 3s. It's a less stable orbital than the 3s orbital is. Because the 3p orbital is less stable, it doesn't require quite as much energy to take away an electron from there as compared to the more stable 3s. Once we move on to silicon and phosphorus, those are also taking electrons from the 3p sublevel, and therefore we start to see that trend increase again in ionization energy. This break in the periodic trend for first ionization energy will typically occur anytime that we see we're going from a full sublevel into a new sublevel. So this happens with aluminum, it happens with gallium. This will even happen from the 4s to the 3d, so like when we deal with scandium or we're dealing with like yttrium, those sorts of elements. The last trend to talk about is electron affinity. Now, electron affinity, the way we define this is the energy change associated with adding an electron to an atom in the gaseous state. Again, we're referencing the gaseous state because it avoids the whole interaction issues that you run into with solids and liquids. Now, at first glance, this looks like it's basically the opposite of ionization energy, because ionization energy is removing the electron and electron affinity is adding the electron. And so you may think like, well, it's just a simple matter of looking at it from the same kind of perspective, just going the opposite direction. The problem is that we find it's a lot easier to take an electron away from an atom than to cram an electron back into the atom. And unfortunately, the quantum mechanic model of the atom makes this a bit complex for us. When looking at a graph of atomic number versus electron affinity, you start to see that there's a lot of inconsistencies in the trend. There is sort of a general trend that we see as we go along each period, where it tends to increase, right? As we go across there, we tend to see an increase in the electron affinity as we go across the groups. But there are a lot of inconsistencies through here. One of the things to notice is that the noble gases keep consistently going down to the bottom of the graph. One of the things, of course, to notice about the graph is that the negatives are going up and the positives are going down. And that's because, if you remember, the negative energy values tend to be the favorable way for things to go. We like to lose energy. So the noble gases keep going into the positive values. That means it actually requires energy to put electrons onto the noble gases. Well, if you think about it, that makes sense, because the noble gases have full valence shells. if you want to add an additional electron to a noble gas, you've got to start a whole new energy level, and that requires a lot of energy input to cram that extra electron in there onto a whole new energy level. We also notice a drop in the electron affinity values of those group 2 elements, so beryllium, magnesium, calcium, strontium, barium. And we're seeing this significantly drop where it's actually becoming very unfavorable to add an extra electron to these. Well, again, if you think about the electron structure of these, beryllium, magnesium, calcium, strontium, barium all have a full s sublevel on their valence shell. That means an additional electron is going to have to get put into the p sublevel on that energy level. And again, p electrons, the p orbitals are less favorable than the s orbitals. So you're putting an electron onto a new sublevel, new type of orbital, that in many cases will require an energy input in order to accomplish that. The last anomaly to look at is when we look at something like column 15, which is your nitrogen, phosphorus, arsenic, antimony. We notice that there's a bit of a problem here where we're getting, again, this drop in electron affinity, meaning that for one reason or another, it's not as favorable to put an electron into those atoms as it is for some of the others. And for these ones, again, what we're going to do is we're going to look at the quantum mechanic model. So let's take nitrogens, for example. When we look at the valence shell of nitrogen's electron diagram, we see the 2 paired up electrons in the 2s sublevel. But then, if you remember, because of Hund's rule, in the 2p sublevel, we're going to have 3 electrons all spinning in the same direction in each of the 3 orbitals. These 3 electrons spin in the same direction because they reinforce each other's magnetic fields. What that means is it makes it a lot harder for an additional electron to get thrown in there that goes against that. So when we throw in this 4th electron into that nitrogen's 2p sublevel, it actually meets some resistance because of the other 3 electrons. And because of that, we're going to see that same issue appear for phosphorus, arsenic, antimony, and all the others that are in that column. And this is why we see the break in the trend when we deal with these elements that have a half-filled sublevel. So in general, as we go from left to right across the periodic table, and those atoms are getting smaller, there's going to be a greater amount of energy released as you add an electron to those atoms, with a few exceptions. These exceptions, again, are when you have to add a new energy level, like in the case of the noble gases, when you have to add a new sublevel, like in the case of the group 2 elements, and when you have to add an electron to a half-filled P, D, or F sublevel, like was in the case of nitrogen, phosphorus, arsenic, antimony. Of the major trends we talk about, electron affinity tends to be the one that's the most tricky because it has the most exceptions. And so generally you just want to have that decent understanding about where is that electron going to go and how does that impact whether or not it's favorable to gain that electron or whether it's going to actually require an energy input to get that extra electron in there.